Welcome friends, Igor is here, and in this video we will talk about similar matrices. In this lesson we will define the notion of similar matrices, construct an example of similar matrices, show that similarity is an equivalence relation, and prove that similar matrices have identical eigenvalues. Let's get started. Suppose A and B are two square matrices of size n, then A is similar to B if there exists a non-singular matrix S of size n such that A is equal to S inverse Bs. We may say the matrix A is similar to the matrix B via the matrix S when it is important to emphasize the role of the matrix S. Here is an example of similar matrices. If we start with a 3x3 matrix B and we take an arbitrary non-singular matrix S of size 3, then we can construct the product S inverse Bs. We can compute the result of this product. This is matrix A, and by our definition, this matrix A is similar to the matrix B via the non-singular matrix S. This example demonstrates one potential advantage to considering similar matrices. Notice that the matrix A has a very simple structure. It is a diagonal matrix. Now we will show that similarity is an equivalence relation on the set of all square matrices of the same size. Let me remind you that a relation is an equivalence relation if it is reflexive, symmetric, and transitive. Suppose that A, B, and C are square matrices of the same size. Then A is similar to A. This means the relation is reflexive. If A is similar to B, then B is similar to A. This means the relation is symmetric. And if A is similar to B and B is similar to C, then A is similar to C. This means the relation is transitive. First, let's prove that the relation of similarity is reflexive. To show that any square matrix A is similar to itself, we need to find a non-singular matrix S that performs this similarity transformation. But in this case, it is easy to see that it is the identity matrix that does the trick. Next, let's prove that the relation of similarity is symmetric. We are going to assume that A is similar to B. This means there exists a non-singular matrix S such that A is equal to S inverse Bs. The matrix S is non-singular, therefore it is invertible. In particular, the inverse of the matrix S is also invertible and therefore it is also non-singular. Let's perform a similarity transformation on the matrix A using the matrix S inverse. The inverse of the inverse of S is the matrix S. Then we are going to use our assumption that A is equal to S inverse Bs. Next comes the associative property of matrix multiplication, and then the inverse property. Multiplication by identity matrix doesn't change anything, so this simplifies to the matrix B. This computation shows that the matrix B is similar to the matrix A via the non-singular matrix S inverse. Finally, let's prove that the similarity relation is transitive. We are going to assume that A is similar to B and B is similar to C. This means there exist non-singular matrices S and R such that S transforms B into A and R transforms C into B. Both S and R are non-singular matrices, therefore the product R times S is also a non-singular matrix. Let's see what happens when we perform a similarity transformation on the matrix C using the non-singular matrix Rs. First, we are going to apply the socks and shoes theorem, which says that the inverse of the product of the matrices is the product of their inverses but written in the opposite order. Then, we are going to use the associative property of matrix multiplication. And next, we are going to use our assumption that B is equal to R inverse CR. But then S inverse Bs is equal to A. This computation shows that the matrix A is similar to the matrix C via the non-singular matrix Rs. This completes the proof that similarity is an equivalence relation. in particular, we prove that this relation is symmetric. So if A is similar to B, then B is similar to A. Therefore, we can say that matrices A and B are similar to each other because this relation works in both directions. Now, let's observe that similar matrices have identical characteristic polynomials. Let's assume that the matrices A and B are similar and the matrix A is equal to S inverse BS. Then we start with the definition of the characteristic polynomial of the matrix A. Next, we replace the matrix A with S inverse BS. Then we observe that the identity matrix is equal to the product S inverse identity S. Next, we use properties of matrix multiplication and we move the scalar multiple x next to the identity matrix. Now you see that we can factor out the matrix S inverse on the left and we can factor out the matrix S on the right. Now we are going to use the property of determinants that the determinant of the product of matrices is equal to the product of their determinants. And now comes the crucial part. The product of determinants is the product of numbers. And we know that the product of numbers is commutative. Therefore, this expression is equal to this. Then, determinant of S inverse times determinant of S is the determinant of the matrix S inverse times S. But this product is the identity matrix. And we know that the determinant of the identity matrix is equal to 1. You should recognize that the last term in this equation is exactly the characteristic polynomial of the matrix B. This computation proves that A and B have the same characteristic polynomial, and in particular, the matrices A and B have the same eigenvalues, because eigenvalues are the roots of the characteristic polynomial of the matrix. Moreover, not only are the eigenvalues of the matrices A and B are equal, but also they have the same algebraic multiplicities, because they are derived from the same polynomial. We proved one implication. If the matrices are similar, then they have identical eigenvalues. But now, does it work the other way around? If two matrices have the same eigenvalues, is it enough to guarantee that they are similar to each other? Let's look at an example. We have 2 by 2 matrices A and B. You can quickly check that they have identical characteristic polynomial, and in particular, they have identical eigenvalues. Now, let's assume that A is similar to B. Then we can find a non-singular matrix S such that A is equal to S inverse BS. But the matrix B is the identity matrix, so the product S inverse BS becomes the identity matrix. But this is impossible because A is not the identity matrix. So this contradiction shows that the matrix A is not similar to the matrix B. So, to be similar, two matrices must have the same eigenvalues, but this is not enough. Then what is the criterion of similarity of two matrices? Well, this criterion involves a more advanced concept of Jordan canonical forms, which is outside the scope of this introductory course. But there is a way to tell whether two matrices are in fact similar. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss matrix diagonalization. I will see you later.